Okay, so we're supposed to write Verilog code to implement this particular function, and it's the sum of the min terms 0, 1, 2, 3, 4, 5, 6. And I was just pointing out that we could simplify this the way we did with problems 1 and 2, but one of the whole reasons for using a language like Verilog is to let it do the simplification for you, because we're not actually going to be building these gates. So we know what these min terms look like. I have them written down here. The reason I have these binary numbers over here on the screen is as I was writing them, I was pointing out that min term 5, if you look at the binary number 5, which is 1, 0, 1, min term 5, that corresponds to x1, x2 not, because that's 0, and x3. So that's what these numbers are doing over there. So this will be a module, and we can call it module problem 3. And our inputs are x1, x2, x3, and our output is f. And then we'll say which ones our inputs are. Those are x1, x2, x3. Our output is f. And then this module is very simple. The only thing we're doing is creating, this f equals all this. And the continuous assign statement, the reason it's called continuous, it's not inside an always block. An always block is not something that happens continuously. This is continuous. This means that, if the signals x1, x2, x3 change, this is going to change. So it's, it's always looking for what the signals are. And and you do it by using the word assign. And I assign f equal to, and then I'll put in parentheses not x1 and not x2 and not x3 or not x1 and not x2 and x3 or, and then you can figure out, that should be or, you can see what the rest of this would be. So that's not much use of my time or your time for me to type it all out, so I just type the rest of this dot 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 and then semicolon and then end the module, and that's all there is to this one. So that's just a reminder of how to use the continuous assign statement, and then just not a semicolon, and then just the note that the reason it's continuous is that it is always updating, unlike an always block. Okay, so any questions on that before we go on? All right, let's look at the next one. You know what? I don't think y'all need this one. I am happy to do it, but it's no different than the one that I just did, really. It's just that it has two outputs. So we would have module problem 4. We have 4 inputs, x1, x2, x3, x4, but we have 2 outputs, f1, f2. So you can have as many inputs and outputs as you want. Your inputs would be x1, x2, x3, x4, and output f1, f2. And then you just assign what your outputs are. So you would just assign f1 equal to, and then you would do just like we did on the problem before. So it'd be x1 and, which I cannot draw an and, not x3 or x2 and not x3, and so forth, and then you would do assign f2, and that would be it, and then end module. So nothing sneaky on that one. So do y'all need me to do anything more with that one, or you pretty much see how that one would work? I will take silence as that you're good with it. Okay. And similarly with this one, I don't think that this is the best use of our time. Write complete Verilog code to implement F1 and F2. Yeah, y'all can do that, right? Right. Okay, let's go on to number 6. Okay, so number 6, this one is a little bit different. So now we are supposed to write a Verilog module to describe this 4x4 multiplier. So if you look at this multiplier, it's got a whole lot going on. And we are going to do some of this. We're not going to do every last bit of this because it gets kind of tedious to do all of it. But we're going to see, what we would do. So when we take a look at this, we see that involved in this are some fast adders. So a fast adder would be a module that was previously written, and in the previously written module, you had let's see. So this was, let me pull it up from your book. I am about as disorganized on my computer as I am on everything else. And this was problem 316. So I'm looking for ladders. Okay, so if you look here, this is from your book. This is the module for full add. So this you would have to put in somewhere else. You could do it as a separate program, or you could do it as part of this program. But you would assume that you had this module available. Weird. I don't know what's going on because I do not know what's going on. Something very strange is happening. One minute. I'm going to try something, see if this works, and be all crazy. Weird. Okay, so y'all can see the screen on my other computer, I'm assuming. And okay, so so here, this was what we were looking at, and then I had copied the text for the full adder, or the code for the full adder on the other computers. I don't have that, but we'll just say that we believe that we do, that code does exist. And when you look at that code for a full adder, what you will see, and this becomes important when you start to use it, is that it had in its declaration, so when it was declared, so it said full add, and it had in the order, it had C in, so that was the carry in, and then X, and then Y, and then S, and then C out. So that part's important because you need to know what order the things are in the other module that you're using, because you're going to be using that module in this program, and you're going to be using it 1, 2, 3, 4, however, 12 times. We're not actually going to write all 12 of them. But, okay, so let's look at this and see what all we would need to implement if we were going to write this all the way out. So first, you can see our inputs go from M0. We have 4 sets of 4 inputs. So it's going from M0 to M3. Are y'all seeing my screen? I just want to make sure.
Yes.
Okay. So you have 4 sets of inputs, so M0 to M3, and so we've got all of those. So when we write this module, you would have module mult, and then you would have M3, comma, M2, comma, M1, comma, M0, and then you need to repeat it again. So now you could use a vectored signal. We'll talk about vectored signals later. That would save a lot of time, but I'm not going to do that right now. So then we would have another number, N3, N2, N1, N0, and then yet another number. So you'd have all of that. Okay, and then your output, if you look at your output at the very bottom here, our output is P0 through P7. So you would have those as your outputs, P0, P1, P2, all the way up to P7. So those would be all your inputs and outputs. And you would put those in there, and you put input, and you would list all of them, and then you do output, and you'd list all of those. Oh, but I'm recording on the other computer, which is not showing on this screen. Okay. Now it's showing. Okay. All right. Okay, so then you would list your inputs and your outputs. Input, output. And then the next thing that we would have to do is, if you look, these are all connected by wires. And so we would have to name all of these wires. So anything that is a connection from one to another that's an internal thing, it's not an input or an output, but it's a signal that we're using internally, you would have to have as a wire. So I could say, I'm just going to make some up here. So let's look at P0 here. M0, let's see. Let's make so M0 and Q0, that's directly an output. So that would be something I would just right away, I would assign P0 equals M0 and N0. Maybe I called this first one M, and the second one is the one I called N. Okay, but then I have, if I look at this output from this full adder right here, that is going into another full adder. So whatever I have here, I have to have that, I have to give that a variable name, and that's going to be a wire. And anything that's not directly an input or an output is going to be a wire. So all of these things right now that I'm tracing, all of these, those are wires. All of that. Every one of those is a wire. So that's right there. That's a wire. That's a wire. All of those things are wires. And so at the top of your program, after you assign your inputs and your outputs, you also will have wires. And so you can count how many of those you're going to have. So you could look and see how many of them you're going to have, and you could give them names. You could call them, W1, W2, W3, and so forth, like that. So let's just take as an example this this bit right here. Okay, so that one I would assign, and let's say that when I draw this out, I would label what I wanted all those wires to be. Let's say that I wanted that wire to be, I called it wire W5. So I would have a line that said assign W5 equal to M2 and what else is that? Q0. Okay, now let's look at what that is going to. So I also have right here, I have this wire. So I could do assign, and maybe that wire's name is W7 equals to, that's my second row of inputs. So this first one I called those M0, M1, M2, M3. When I put these in the program, I called these N's. So I would say assign W7 N1 and Q1, and that's this AND gate right here. And so now I have, did I do the wrong one? I did do the wrong one. I wanted to do N1. No, I did the right one. That was N1. So I did this one right here. So that AND gate. So I have this wire, I have the green wire right here, and I have the red wire. And all of that was to get us to the point that we were ready to use the full adder. So now what we would do is we would assume we had this other module already written. So we had this other module that was called full add. Well, I have that written right up here. So full add. So now I want to use a full adder. So to use that full adder, I write full add, because that was the name of my module, full add, and then I give it a name, and I can call it whatever I want to call it. I'll call it, let's say it was the third adder that I had put in. So this will be, by the time I get to it, I'll call it adder 3. And then when I put the stuff into it, I have to put it in the right order. So I have to say what is coming in on each one. So on this full adder, it's the carry in is coming in on the left. That's the CN. I didn't say what that wire was named. Let's say that one is named wire 9. So I need to put that one first. So that one would be W9, because that's our carry in. Then the next two are the things that I am actually putting in there. And those are W5 and W7. So W5, comma W7. And then the next things that I'm going to get are the sum and the carry from this particular adder. And so I would have names for those as well. And these would also be wires, but maybe I have different names for them. It's this. So I have this wire right there, and I have this wire right here. So I would have whatever names I had for those wires. Maybe I had them named S1 and S2. Okay, so then you'd go through, and I'm absolutely not going to do all of this, but you would go through and you'd label all of these things as wires, and you'd make all of your ands, but it's just when you put in the adders, the way you put them in is you put in full add, because that's the name of your module, and then you give it a name, and then you put all its inputs and outputs, and then you're ready to go. So, all right. So, like I said, if I were to do this from scratch to start over, I might do them as vectored inputs, vectored signals, but it still wouldn't matter because I'd still have to deal with each component separately. So even if I had M as a 4-bit vector, so even if I had it as a vector, 0 to 3, I still would have to individually get to M0, M1, M2, and M3. So I'm not sure the vectored signals would help me a lot with that one. Okay, so are there questions on that before we go on to the next thing?
Yeah, I had a question.
Sure.
I was confused on the adder. So, like, within the adders is within each gate that's gonna be like the wires connected to it.
Yeah, so this particular program is using adders. So it's like when we draw a circuit and we had an AND gate or an OR gate, and we know how to write those in our code. So if I wanted this variable to be W, then in my code, and this was A and this is B, then in my code I would say assign W equal to A and B, and that'd be fine. So if instead I want to get an adder, so I have an adder and I have code for an adder, and the way an adder works is it has two inputs, I'll call them X and Y, and it also, it has three inputs really if it's a full adder. You also have a carry, and it has two outputs. This is the carry in, and it has two outputs. You have the carry out, and you have the sum. So that's the way an adder works. And you don't want to write all of the code for an adder every time you put an adder in there. You only want to write it once. And so you use the code for an adder as a separate module. You write that as a separate module, and that's already stored somewhere else. Or you could have it in the same program. But then when it's stored in that other program, it has the name, the module has the name full add, and in its definition, it has what did I say it had? C1 X Y S and C out. And so when I put my adder into my circuit, so now when I have a circuit and my circuit has an AND gate and the result for that AND gate is an input into a full adder, so I have A, B, and I have C over here, and I have my carry in is coming in from somewhere else, maybe that's D, and I have my sum and I have my carry out. So when I want to use that in my circuit, then all I do to use it is I would say, okay, well now I want to have a full adder, and so I don't actually use an assign statement. So instead, I would have full add, and then I'd name it whatever I want to name it. So this is my adder. And then I just list the things that are coming into it in the right order. So first I put my carry in, and then let's say that I had called this F. So D, and then F, and then C. And then I have my outputs, which are S and C out. And now I can use S and C out elsewhere in my program. So if I needed to, I could assign, X equal to S and something if I needed to. S and, I don't know, S and, I can't do an and symbol. S and Y if I needed to. Did that answer your question?
Yes.
Okay. All right. Okay. So I'm now going to stop this recording and save it.